This is lecture 8.5, which is about Le Chatelier's principle. As usual, please make sure that you've completed the learning targets, which are shown here as well as on Canvas, prior to watching this lecture. You don't need to get a lot of detail, you just need to know what you're expecting to hear me say so that you can add some more specific information as you watch. And when you're ready, go ahead and stop the video and restart it when you're done. Okay, here we go. So Le Chatelier's principle is the idea that once a system is at equilibrium, unless it's disturbed, it will stay at equilibrium. And if a system is disturbed once it's at equilibrium, then the reaction, the forward or the reverse reaction, will occur faster, one or the other in most cases, will occur faster in order to counteract what the disturbance did, right? So you want to remember that whatever the experimenter does or the external conditions do that might change the equilibrium, the reaction will act to reverse that, okay? So some of your disturbances that you should have encountered in your learning targets would be things like changing the concentration or the pressure by adding or removing a substance that's a part of the reaction, adding a gas or an inert substance, something that's not part of the reaction. This is key. It doesn't really have to be an inert gas. It could be adding something that's not part of the reaction. You can change the volume, which, remember, in gas laws changes the pressure. So remember that as volume increases, the pressure inside the container of the gases decrease. And so we want to keep that in mind. And then you can change the temperature and you can add a catalyst. You will discover as we're talking through this lecture that the only one of these that will change K is changing the temperature. Oops, changes the equilibrium constant K. All right, that's the only one. And then all the other ones have no effect on the equilibrium constant. So that's really important. Something that you need to get used to is the idea that a reaction shifting because of this is really saying that temporarily it proceeds faster in one direction until it's reaches equilibrium again, and then the forward and reverse rates will be equal. So you just kind of want to picture it's doing the opposite of what you did. All right, so the first thing I want to talk about is changing the concentration or pressure by adding or removing reactants or products. You need to know and you need to remember that the state of matter makes a difference. Anything that's not in your equilibrium constant cannot have an effect. So solids and liquids, adding them or removing them has no effect. And this is really important. So as long as there's some there and the reaction can occur, then you are looking at no effect at all on the equilibrium position, no shift to the left or the right on the equilibrium position because of adding or removing solids and liquids. This means we're focusing on aqueous and gases, just like we do for everything else in equilibrium. And remember, the reaction is going to do the opposite of what you do. So if you add more, the reaction shifts to use it up. This is easier than remembering add a reactant, go to the right, add a product, go to the left. Just remember that if you add more, the reactant goes to use it up. And if you remove it, then the reaction shifts to make more of what you've just taken out. So how do you do that? I need you to think through this just a little bit, that adding or removing, adding is easy. We can very easily usually add things to a reaction, but removing things is really difficult, and we have to do it usually by reacting it out. So we have to add something that will react with a piece of our reaction. So up here on this slide where I said you can add an inert gas that's not part of the reaction, it also can't react with anything in the with anything that's present, okay? So if something reacts with something, then it's removing it, and that's a really important thing that you need to picture, because otherwise you can't just reach in there and pull something out in most cases, because we're talking about aqueous and gases here. I can't pull out ions in solution, or I can't pull out gas particles. So that's the thing that you want to keep in mind. And what you do need to know is that the pressures and concentrations won't be the same as they were when you added or before you added or removed, but they will still be in the same ratio. So I want you to look at this graph because it's really important to see what this graph looks like. Clearly, at this point, this reaction is at equilibrium. The concentrations are not changing. And I can tell that I added H2 right here because of this very quick shift in concentration or pressure of, this is concentration, so concentration of H2. And then I see a gradual shift in its concentration and a gradual shift in the concentration of N2 and a gradual shift in the concentration of NH3. And notice that the NH3 is a product and it's increased here until it reaches equilibrium again. And that the N2 and the H2 are the reactants and they've decreased here until it again reaches equilibrium. Okay, so notice that if let me erase all my scribbles here. If I add H2, I've added H2 and the reaction needs to shift to use it up, which means it will form more NH3 and it will have to use up the N2 and some of the extra H2 that I added. So notice that the N2 decreases because I'm using it and I didn't add any extra in, and the NH3 increases because I'm forming it and I didn't remove any or add any more in, so it increases gradually. But the H2, after this initial increase, decreases also, but when we're finished, it still ends higher than we started with, and that's because there was more in there to start with. Okay, so you want to kind of picture what's happening there. There's another example here that I can show you where we're removing something. So notice that this part right here where the CO2 drops in a hurry, I must have removed CO drops in a hurry. I must have removed that. Since I'm removing this, the reaction needs to shift to make more. We need to increase that again. So it's going to shift to the right. And when it does that, it's going to increase the amount of O2 and decrease the amount of CO2, right? Because this will have to go up and this will have to go down. And notice that I removed this and it's going to go up from where it was after I removed it, but not back up to where it was when I started. Okay, so you have to picture what's happening theoretically so that this works for you. So one more quick example that includes a couple of different things so that you can kind of see what's happening. In this question, you always want to look and make sure for solids and liquids. So I see that these two are solids, okay? And they want to know how the equilibrium position will shift. So usually we talk about this as a left or right, or toward, to form more, you can say, to form more. Left would be to form more reactants, or right would be to form more products, right? So you kind of want to just picture, there's a couple different ways that we can say that, but we usually say left or right versus forward and reverse, or we say form more of the reactants or the products. So adding argon gas is the first one, and argon gas is a noble gas, so I can look at my equation here and see that argon's not going to react with anything. So I didn't talk about this up here, it was in your reading, but adding an inert gas, I know it increases the total pressure in the container, but remember that what we put into our equilibrium constant is the partial pressures of the gases that are in there. All right, so adding another gas does not change the partial pressure of the other gases in our system. And so adding an inert gas has no effect. So part A is no effect. All right, part B says you're going to add NaHCO3 solid, so sodium bicarbonate solid. I don't care if I have a lot of solid or a little solid here, it's a solid, and it's not in my equilibrium constant. For this, the equilibrium constant, Kc or Kp, would include only the CO2 and the H2O, whether it's Kc or Kp, so I'm not putting brackets or pressures, just know that. The other two, it would be over 1, and the other two are solid, so they wouldn't be there. So B is also no effect. All right. Now, the next one is a little tricky. You're going to add MgClO4 twice, so you're adding magnesium perchlorate. And they tell you it's a drying agent that removes the water. So the water is a gas, and if we remove the water, the reaction will have to shift to fill it in. So C has an effect of shifting to the right, or to form more product. All right. If they ask you about the pressure of the CO2, it would go up. If they asked you about the amount of NaHCO3 and Na2CO3, they would change. This would go down and this would go up. But changing them does not affect the equilibrium. So that's an important distinction. And then finally, the last one is dry ice is added. And so you need to know that dry ice is solid CO2, but remember that the first thing that dry ice does at regular atmospheric temperature and pressure is sublime. So even though we're adding solid CO2, it's going to add CO2 gas to our system as it sublimes, even if the temperature is constant. So this means that I'm adding CO2, which means the reactant needs to use it up and bring it back down. So it's going to have to shift to the left. So for part D, we're going to shift to the left or to form more reactants. So that's how you cope with concentration or pressure changes because of adding or removing things that are a part of your reaction. All right, so the next one I want to look at is what happens if you change pressure by changing the volume. So remember that anything that changes the partial pressures, anything that changes the pressures of those gases is going to cause a shift in the system. So if I add more gas, clearly that changes the partial pressure, but I can also change the partial pressure by, let me say that again. If I add more of one of the gases that's part of my reaction, then that will shift to use it up because it's like adding concentration. But if I change the volume, that also changes the pressure. So remember, according to the ideal gas law, as volume increases, pressure decreases. And as volume decreases, sorry, I should put these in the right place for my lecture. As volume increases, pressure decreases, and as volume decreases, pressure increases. And so what you need to remember is that the reaction is going to do the opposite of what you make it do. It will try, but if the moles of gas on both sides are equal and the change in moles of gas is nothing, then is zero, then the reaction will not be able to counteract this. Okay, so we can look at this and see that in this case, there's a change, which means this reaction, this case here, there's a change, which means that this reaction must have different moles of gas on each side of your arrow. So if I look at this and we say that SO2 plus O2 is at equilibrium with SO3, then what's happening is that we notice that this is not a balanced equation and we would need to double the SO3 and double the SO2, and that gives us 6 O's on each side now and 2 S's. So notice that this clearly, the delta Ng for this is products minus reactants, or 2 minus 3, which is -1. So this definitely has a change, which means that we need to talk about how that works. If the change in moles of gas is 0, then the pressure will increase or decrease, and there will be nothing the reaction can do to counteract it. Okay, so the partial pressures would increase or decrease. You're not changing the amount of gas, you're just changing the number of collisions with the walls. Okay, but if there's a difference in the number of moles, now the reaction can shift to try to counteract what you've done. So if you increase the pressure, in other words, you decrease the volume and you increase the pressure, the reaction's going to try to proceed in the direction that will decrease the pressure again, which means that it's going to go toward the side with fewer moles of gas. Okay, so notice that this is like the example that we see here, that when the volume of the container was decreased, the pressure of all 3 gases increased. Okay, and so when we look at that, then they all will have to. We'll have to try to counteract it. So if it goes to, I want you to just illustrate what happens here. If it shifts to the right, it will form 2 moles of gas, right? If it shifts to the right, it will form 2 and use 3, which means eventually the pressure will decrease because it's going to use more than it forms, okay? If this reaction shifts left, in this case, it's going to form 3 and use 2. And so eventually the pressure would increase from where we are. So if by decreasing the volume we increase the pressure, the reaction needs to decrease it again. It's going to shift to the side that has fewer moles of gas. Remember, this lovely picture here will help you. More gas equals more pressure. And so if you've caused the pressure to go up, then the reaction will shift to make the pressure go down by creating less gas. And the opposite occurs if the pressure decreases. All right. Again, remember, K does not change. They come back to the same ratio that they used to be, so K does not change. Okay, so let's look at a couple of examples quickly so you can see what's happening here. We want to predict the effect of increasing the container volume. So the first thing I need to remember is that when volume increases, pressure decreases. All right, so I need to decide which direction these reactions will shift to make less gas. Sorry, the pressure decreases. So the reaction will need to increase the pressure again. All right, so it's trying to counteract what I've done. It wants to normalize it back to where it was. So now it's going to shift toward more gas. Okay, so this is what you're thinking. So when you look at these, be really, really careful. If you're not paying attention to states of matter, you're going to think that the number of moles on each side in part A are equal, but they're not. This is a liquid. So I have 0 moles of gas on the left and 1 mole of gas on the right. If the reaction is trying to increase the pressure because I lowered it, then it's going to shift to the right. Okay. I look at the second example here, and again, the volume has increased, so the pressure's decreased. The reaction wants to increase the pressure again. Don't say wants to in your free response. Say the reaction shifts to increase the pressure again, making more gas. So all of these are gases. So notice that this side has 2 moles, and this side has 4 moles of gas. So if the reaction needs to increase the pressure again, this one is also going to shift to the right. Let's do some decreasing ones. If I decrease the volume, that means the pressure inside goes up, which means the reaction needs to decrease the pressure again. It needs to take it back to normal, back to where it was. And it may not decrease completely. Notice in my graph up here, the increase or decrease doesn't take it back necessarily to where they were. You have to kind of picture that, okay? And we're going to increase something that might not have been increased before. But we want to try to decrease the pressure again. So let's check states of matter. This is a liquid, so ignore it. All right. Decreasing the pressure means shift to where there's less gas. All right. So this side here has 6 moles, and this side here, because that's a liquid, has 3 moles. And so less gas means that this one would shift to the right. This one, they're all gases, so I can count. This is 7 moles. And this is 8 moles. If it's going to shift to the side with less gas, this one's going to shift to the left. All right, so that's 2 of them. Let's keep going. Changing the temperature is the only one that changes K. So this is a little bit more involved. So we need to notice that this happens because of the activation energies in the forward and reverse reaction being different. When you change the temperature, the way that it permanently changes the forward and the reverse rates is different. Increasing the temperature increases them both, but increases the endothermic direction more. And decreasing the temperature decreases both, but decreases the exothermic reaction less. It's weird, okay? So you have to kind of really think carefully about how this works. But because what this is doing is changing those forward and reverse in different ways, now it's going to come out at a different ratio of products and reactants when you're finished. So this is what causes a temperature change causes a K change. Okay, the things that you want to remember that will help you is increasing the temperature favors the endothermic direction, and decreasing the temperature favors the exothermic direction. So I give you a really big hint here that you want to add the heat to the appropriate side of the equation to visualize it. Okay, so you see what happens here, and in order to identify if K is increasing or decreasing, you have to decide who's going to be favored. Okay, so notice that both of these graphs are showing a temperature decrease, and in this one, the energy is on the right, It's a product, so this reaction is written as a negative delta H, or as an exothermic reaction. And in this one, the energy is on the left, so it's a reactant. So this is a positive delta H, or an endothermic reaction. So notice that if the temperature is decreased, this is going to favor the exothermic direction. Well, on this one, that's easy. On this first one, the exothermic direction is the direction that it's written on your paper. So when I decrease the temperature, it's going to shift to the right. But on this one, it's an endothermic reaction. If I decrease the temperature, it actually is going to go in the reverse direction, which is the exothermic. If forward is endo, remember reverse is exo, okay? And so it's going to shift to the left. And you can see this because what we see here is the CO2 increases and the CO and the O2 decrease. Whereas over here, it's shifting to the right, so the SO3 increases and the other two decrease. Okay, so this seems really, really complicated. I do want you to notice that if the products of this, if this one here, when it shifts to the right, we're increasing the products and decreasing the reactants permanently. And so because the K is products over reactants, because these go up and this goes down, K will increase in this case. Okay, in this case, because of my shift, we're going to look at K as products over reactants, but in this case, my reactants increase and my products decrease. And so both of those mean that K overall, in this case, would decrease. And so you have to be super careful and think about this, all right? If you're explaining it, you need to explain it as in increasing the temperature favors the endothermic direction, or decreasing favors the exothermic direction. That's your explanation. Okay, you don't need more than that. But if you're doing this and you're trying to decide which way that is and you want to kind of picture it, then pretend that heat is a reactant or a product. And adding heat means the reaction will have to use it up. So if you have heat on the left of your equilibrium arrow and you add heat, you increase this, the reaction has to shift to use it up. The same thing happens if you think about removing heat. Then the reaction will have to fill in what you removed. So if you lower the temperature of this, you've removed heat, and the reaction will have to shift toward the heat to fill it in, okay? Just the same way that you figured out what happened up here, all right? So up here, sorry, concentrations. So just kind of think about that so that you can kind of use that as a cheat way. You can't explain it. You have to explain it like this, but you can use that as a cheat way. So let's do a couple of examples. Predicting the effect of increasing the temperature on the amount of products in the reaction. So the first thing I need to notice if I'm increasing temperature is I need to decide if these are endothermic or exothermic. So negative delta H is exothermic, so this one has the heat on the right side. Increasing the temperature means it's going to use up the extra heat. This is what you have to remember, okay? Increasing the temperature favors the endothermic direction. All right, so it's going to use up the extra heat. So if the heat is on the right in this equation, then the reaction is going to shift to the left to use it up. All right, let's do another one. This one's a positive delta H, which means that this is an endothermic reaction as it's written, so the heat is on the left. So increasing the temperature means it's going to use up the heat and shift to the right. All right, so in this case, if I've shifted to the right, K will increase. And in this case, if I've shifted to the left, K will decrease. Again, shifting up here doesn't change K, but shifting temperature changes K. All right, so let's do one where we're changing a decrease in temperature. So remember that now I want to picture this as removing heat, and a decrease in temperature favors the exothermic direction. So this reaction's exothermic, which means the heat is on the right, and if I've decreased it, I have removed heat, and the reaction has to shift to add it back in. So the exothermic direction is the direction this reaction is written, so this is going to shift to the right. When it shifts to the right, K will increase. Okay? And if I look at the other one, this is an endothermic reaction, so the heat is here. And if I remove the heat, the reaction has to fill it back in, so it will shift to the left, and when it does that, K will decrease. Okay, so there's one more way we can look at this, and I really like the pictures because I think you're going to see them on the AP exam. So in this case, we have the reaction. Notice the NH4Cl is a solid. So this is your solid in the bottom of your beakers. And then we have forming at equilibrium with NH3 gas and HCl gas. So here's your HCl and here's your NH3. All right. Notice that this reaction is endothermic. So I'm going to come over here and write plus heat so that I can picture what's happening here. Okay. They want to know now which one shows me the mixture at the highest temperature, right? Well, if the temperature's high, I've added heat, the reaction's going to shift to the right. So in this case, I need to know which one has the most product. So that's pretty easy. I can do this even without counting. This would be this one. So this is your answer to part A. Okay. And then they want to know which one has the lowest temperature. So the lowest temperature would mean I'm removing heat, and it's going to shift away from the products or toward the reactants. And so you can't really notice that the solid looks any different, but you can definitely see that this one has fewer molecules of ammonia and hydrochloric acid or hydrogen chloride gas. So A would be your answer for part B, because it's shifted to try to add heat back in, and in the process of doing that has used up the NH3 and the HCl. Okay? All right, so only a little bit more. Oh, I didn't talk about the Van Hoff equation. This is like the Arrhenius equation in rate, only it's for equilibrium constants. I need to show it to you. Notice that this is the delta H. Notice that this R is the 8.314 joules per moles Kelvin, because it's your energy R. And these are temperatures, they must be in Kelvin, right? And these are your equilibrium constants. So I don't think you'll need to use it, but I wanted to show it to you so that you've seen it before. All right, and then finally, adding a catalyst. This is the last piece of this. Adding a catalyst has zero effect on an equilibrium system. This is kind of confusing, but you have to remember that adding a catalyst lowers the activation energy in both directions. And so it speeds up the forward and the reverse. And because it's speeding them both up, it's speeding them both up in a similar way. And the concentrations and the pressures of the reactants and products remain the same. Basically, we would say it reaches equilibrium sooner, but it has no effect on the concentrations and no effect on the K. All right. So in contrast, a reminder that in rate, when we're talking about the lowercase k, the rate law constant, adding a catalyst increases it because we've increased the rate of the reaction. And changing the temperature will change the rate law constant. So increasing the temperature increases the rate law constant. Decreasing the temperature then decreases the rate law constant, right? So both adding a catalyst and changing the temperature will change the rate law constant. But the only change, you have to remember this, the only change that affects the equilibrium constant, capital K, is a change in temperature. Only change, all right? So hopefully this was helpful. You have lots of examples, and we'll practice this in class. Come ready, and I'll see you soon.